Hello, welcome to our comprehensive journey into the world of electromagnetism. In this video, we're going to explore the fundamental principles that govern electric and magnetic interactions. We'll be covering several key topics. First, we'll dive into electric forces and fields. Here, our goal is to understand how charged objects interact. Next, we'll explore electric potential and voltage, which describes the energy associated with electric fields. Then we'll investigate capacitors and capacitance, devices that are fantastic at storing electric charge and energy. After that, we'll build electric circuits, focusing on how charges move and interact in closed loops. And finally, we'll wrap things up with magnetism, the counterpart to electricity, and see how the two are intimately connected. By the end of this lesson, you will be able to solve problems involving electric forces, calculate electric fields and potentials, understand and analyze simple circuits, and work with magnetic forces. We'll do this by breaking down complex ideas into manageable steps and focusing on the physical meaning behind all the formulas. Let's begin with our first topic, electric forces and fields. The learning objectives here are to describe electric charge and its conservation, understand and apply Coulomb's law, and define and visualize the electric field. The most fundamental concept is electric charge. We all know opposites attract and likes repel. That's charge in action. There are two types, positive charge and negative charge. An electron is a fundamental unit of negative charge, and a proton has an equal amount of positive charge. It's important to remember that charge is conserved. It can't be created or destroyed, only moved around. So, how do we calculate the force between two of these charges? This is described by Coulomb's law. Coulomb's law is given by the formula F equals K times the absolute value of the product of the two charges, Q1 and Q2, all divided by the square of the distance, ER, between them. Let's break that down. F is the magnitude of the force. Q1 and Q2 are the amounts of charge. R is the separation distance. And K is Coulomb's constant, a very large number that makes the math work out. The most important part of this equation is the 1 over r squared dependence. This means that if you double the distance between the charges, the force becomes 4 times weaker. If you have the distance, the force becomes 4 times stronger. Now, let's look at the concept of the electric field. You might wonder how one charge knows the other is there to exert a force. Scientists introduced the idea of an electric field as a kind of aura that surrounds every charge. This field is a way to describe the space around a charge. If you put a test charge, Q0, into this field, it will feel a force. We define the electric field, E, at a point as the force, F, that a tiny test charge Q0 would experience there, divided by the test charge itself. This means that the electric field at a point is simply the force per unit charge. Its unit is newtons per coulomb. We can also write a formula for the electric field produced by a single point charge. The magnitude of the electric field, E, created by a charge Q at a distance r is K times the charge Q divided by r squared. Notice this looks very similar to Coulomb's law. That's because it is. It's just Coulomb's law divided by one of the charges. We visualize electric fields with electric field lines. These lines point in the direction of the force a positive test charge would feel. For a positive charge, the lines point radially outward. For a negative charge, the lines point radially inward. All right, let's work through an example to solidify our understanding of Coulomb's law. Let's say we have 2 point charges. The first, Q1, has a positive charge of 2.0 microcoulombs, or 2 times 10 to the negative 6th coulombs. The second, Q2, is negative, with a charge of negative 4.0 microcoulombs, or negative 4 times 10 to the negative 6th coulombs. They are separated by a distance r of 3.0 meters. The question is, what is the electric force on each charge? First, let's think about the direction of the force. Since we have a positive charge and a negative charge, they will attract each other. So the force on Q1 will point towards Q2, and the force on Q2 will point towards Q1. Now, let's calculate the magnitude of this attractive force using Coulomb's law. We plug in our values. Coulomb's constant K is 8.99 times 10 to the 9th. For the charges, we take the absolute value, so we have 2 times 10 to the negative 6th and 4 times 10 to the negative 6th. And the distance is 3.0 meters, so we divide by 3.0 squared. Let's calculate step by step. The product of the charges is negative 8 times 10 to the negative 12th. Taking the absolute value, we get positive 8 times 10 to the negative 12th. The distance squared is 9. Now we multiply 8.99 by 8 and divide by 9. This gives us about 799. So the force is approximately 7.99 times 10 to the negative third newtons, or about 8 millinewtons. Because of Newton's third law, the force on Q1 due to Q2 is exactly the same magnitude as the force on Q2 due to Q1. They just point in opposite directions. Therefore, the electric force on charge Q1 is 8 millinewtons towards Q2, and the electric force on Q2 is 8 millinewtons towards Q1. Now, let's explore our second topic, electric potential and voltage. Think of this as the energy side of electromagnetism. Our goals here are to define electric potential energy, understand the concept of electric potential or voltage, and be able to calculate it for simple charge distributions. We know that a charge experiences a force in an electric field. Just like an object in a gravitational field has gravitational potential energy, a charge in an electric field has electric potential energy. Electric potential energy, which we'll call U, is the energy a charge has due to its position in an electric field. The change in this energy when we move a charge from one point to another is equal to the negative of the work done by the electric field. While potential energy is useful, it depends on the size of the charge you're using. A more universal concept is electric potential, or voltage, denoted by V. Voltage is defined as the potential energy per unit charge. In other words, it's the amount of energy that each coulomb of charge would have at a specific location in an electric field. The unit for potential is the joule per coulomb, which we call a volt. Voltage is a scalar quantity, which means it only has a magnitude, not a direction. It describes the electrical pressure at a point in space. Just as water flows from high pressure to low pressure, positive charge flows from high voltage to low voltage. We can write down the formula for the voltage created by a single point charge Q at a distance r. The voltage 5 is K times the charge Q divided by the distance r. This looks similar to the electric field formula, but notice the differences. First, there's no absolute value sign. The sign of the charge Q matters. Second, it's r in the denominator, not r squared. This means voltage decreases with distance at a slower rate than the electric field. This formula allows us to calculate the electrical potential at any point in space around a charge. The potential is positive near positive charges and negative near negative charges. Let's apply our knowledge of electric potential to a practice problem. Consider the same two charges from our previous example. A positive charge Q1 of 2 microcoulombs and a negative charge Q2 of negative 4 microcoulombs, separated by 3 meters. This time, we want to find the electric potential, or voltage, at the midpoint between them. First, let's understand the geometry. The total distance is 3 meters, so the midpoint is at 1.5 meters from each charge. Now, electric potential is a scalar quantity. This is a huge advantage over force or field calculations. It means we don't have to deal with vectors and directions. We can just calculate the potential from each charge at the midpoint and add them up. Let's call the potential from Q1 at the midpoint V1 and the potential from Q2 at the midpoint V2. The total potential V will be their sum. V equals V1 plus V2. Using our formula V equals KQ over R. The potential from the positive charge, V1, is K times Q1 divided by 1.5 meters. The potential from the negative charge, V2, is K times Q2 divided by 1.5 meters. Let's plug in the numbers. V1 is K times 2 microcoulombs divided by 1.5 meters. V2 is K times negative 4 microcoulombs divided by 1.5 meters. Notice the negative sign for Q2 is included in the calculation. To find the total potential, we add these two values. V equals V1 plus V2. We can factor out the common terms K and 1.5 meters. We are left with K over 1.5, multiplied by the sum of the charges. The sum of the charges is 2 minus 4, which is negative 2 microcoulombs. So V equals K times negative 2 microcoulombs, all divided by 1.5 meters. Plugging in K, we get 8.99 times 10 to the 9th, times negative 2 times 10 to the negative 6th, divided by 1.5. This calculation gives us negative 1.199 times 10 to the fourth volts. We can round that to negative 12 kilovolts. The negative sign is significant. It tells us that this location in space is at a lower electrical pressure, or potential, than if the charges weren't there. Let's move on to our third topic, capacitors and capacitance. You've encountered capacitors in everyday electronics, like in camera flashes and computer memory. In this section, you'll learn to describe how a capacitor stores charge, calculate its capacitance, and understand the energy it stores. So what is a capacitor? At its core, a capacitor is just two conductive plates, or conductors, separated by an insulator. How does it work? Let's connect it to a battery. The battery's positive terminal pulls electrons off one plate, making it positively charged. It pushes these electrons onto the other plate, making it negatively charged. The insulator between them prevents the charges from flowing together. This separation of charge creates an electric field between the plates, and therefore, a voltage difference across them. The capacitance, C, is a measure of how much charge, Q, a capacitor can store for a given voltage, V, across it. The formula is C equals Q over V. The unit for capacitance is the coulomb per volt, which we call a farad. A farad is a very large unit, so you'll more often see microfarads or nanofarads. Capacitance is a property of the capacitor's geometry. For a simple parallel plate capacitor, we can calculate its capacitance using a few physical parameters. For a parallel plate capacitor, the capacitance C is equal to a constant called epsilon naught, multiplied by the area of the plates, A, and divided by the distance, D, between them. This formula makes intuitive sense. Larger plates mean more area to store charge, so capacitance increases. Bringing the plates closer together decreases the voltage for a given charge, which also increases capacitance. The constant epsilon naught is related to the material between the plates or the dielectric. Since a capacitor stores charge, it also stores energy in the electric field between its plates. The energy stored, U, can be calculated in a few different ways. 1/2 CV squared, 1/2 QV, or Q squared over 2C. All of these formulas are equivalent and represent the work done to charge the capacitor. Let's work through an example involving capacitance and energy. Imagine we have a capacitor with a capacitance of 10 microfarads. This capacitor is connected across a 12-volt battery. We want to find two things. First, the charge on each plate, and second, the energy stored in the capacitor. First, let's list what we know. We know the capacitance C is 10 microfarads, which is 10 times 10 to the negative 6th farads. And we know the voltage V is 12 volts. Our first goal is to find the charge Q. We can use the fundamental definition of capacitance, C equals Q over V, and rearrange it to solve for Q. So Q equals C times Vi. We just need to multiply the capacitance by the voltage. Plugging in our values, Q equals 10 times 10 to the negative 6th farads, multiplied by 12 volts. This gives us 120 microcoulombs. This means one plate has a charge of positive 120 microcoulombs, and the other has a charge of negative 120 microcoulombs. Now for the second part, finding the energy stored. We have three equivalent formulas, and we can use any of them. Since we have C and V, the easiest is to use U equals 1/2 C of V squared. The energy stored, U, is 1/2 times the capacitance times the voltage squared. Let's substitute our values. U equals 1/2 times 10 to the negative 6th farads times 12 volts squared. 12 squared is 144, so we have 1/2 times 10 to the negative 6th times 144. This calculation results in 720 microjoules. This is the amount of potential energy stored in the electric field between the plates of the capacitor ready to be released. Our fourth topic brings us into the realm of electric circuits. This is where we see electromagnetism in action, creating power and controlling devices. In this section, you'll learn to define electric current, understand Ohm's law and its relationship to resistance, and calculate the total resistance for circuits with resistors in series and in parallel. An electric circuit is a closed loop that allows charges to flow. We use a battery to provide a potential difference, or voltage, which pushes the charges around the loop. This flow of charge is what we call electric current. Electric current, I, is defined as the rate of flow of electric charge. That is, the amount of charge Q that passes a point in a wire per unit time. T, the unit of current, is the coulomb per second, which we call an ampere, or just amp. The battery provides the voltage, or electrical pressure, and the wire allows the current to flow. But sometimes, we want to control the amount of current. We do this with a component called a resistor. A resistor, as its name suggests, resists the flow of charge. The property of a material to resist current flow is called resistance, R. Now, how are voltage, current, and resistance related? They are connected by one of the most famous and fundamental laws in electricity, Ohm's law. Ohm's law states that the voltage phi across a resistor is equal to the current I flowing through it, multiplied by its resistance R. You can also write this as I equals V over R, or R equals V over I. This law is incredibly powerful. If you know any two of these quantities for a resistor, you can find the third. We often need to combine resistors in circuits. There are two main ways to connect them, in series and in parallel. In a series circuit, resistors are connected one after another, creating a single path for the current to flow. In this case, the total or equivalent resistance, R-equiv, is simply the sum of the individual resistances. In a parallel circuit, resistors are connected to the same 2 points, creating multiple paths for the current. Here, the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistances. For just 2 resistors in parallel, a handy shortcut is to use the product over sum rule. R-equiv equals R1 times R2 divided by R1 plus R2. Let's put these circuit concepts into practice with an example. Consider the circuit shown here. We have a 12-volt battery connected to a combination of resistors. Our goal is to find the total or equivalent resistance of the circuit and the total current that the battery provides. We need to simplify this circuit step by step. Let's label the resistors R1, R2, and R3. Notice that R2 and R3 are connected in parallel. The first step is to combine the 2 parallel resistors. Remember the product over sum rule? R-equiv 1, the equivalent resistance of just the parallel part, is 2 times 6 divided by 2 plus 6. That's 12 divided by 8, which gives us 1.5 ohms. So, this parallel combination of a 2 ohm and 6 ohm resistor acts like a single 1.5 ohm resistor. Now our circuit looks much simpler. The equivalent resistor of the parallel combination is in series with the 8 ohm resistor R1. The circuit has been reduced. Now we have an 8 ohm resistor in series with our new 1.5 ohm resistor. For the second step, we combine these 2 series resistors to find the total equivalent resistance, Req. Since they're in series, we just add them up. Req equals 8 ohms plus 1.5 ohms. This gives us a total equivalent resistance of 9.5 ohms. This means the entire resistor network draws the same current as a single 9.5 ohm resistor. Now we can use this total resistance to find the total current flowing from the battery. We'll use Ohm's law for the entire circuit. The total current, I total, equals the battery voltage, V, divided by the total resistance, Req. Plugging in our values, I total equals 12 volts divided by 9.5 ohms. This gives us approximately 1.26 amperes. So, a current of 1.26 amps flows out of the battery and through the 8 ohm resistor, before splitting between the 2 ohm and 6 ohm resistors. Our final topic connects everything we've learned to the other half of electromagnetism, magnetism. In this section, our goals are to describe the magnetic field produced by moving charges and currents, and to calculate the force on a charged particle moving in a magnetic field. It's a common misconception that electric charges and magnetic poles are the same thing. They are not. An electric field is produced by a charge. A magnetic field, on the other hand, is produced by a moving charge. Think of a current in a wire. That's a stream of moving charges. This current creates a magnetic field that loops around the wire. We define the magnetic field with the symbol B. Its unit is the Tesla. So we've seen that a stationary charge creates an electric field, and a moving charge creates a magnetic field. This is the first connection. The second connection is what happens next. If a second charge, also moving, enters this magnetic field, it will feel a force. This is described by the magnetic force law, or the Lorentz force. The force, F, on a charged particle Q, moving with a velocity v in a magnetic field B, is given by F equals QV B sine theta. Let's break this down. Q is the charge, V is its speed, and B is the strength of the magnetic field. Theta is the angle between the particle's velocity vector and the magnetic field vector. The sine theta term tells us something very important. The magnetic force is greatest when the particle moves perpendicular to the magnetic field. The force is zero if the particle moves parallel or anti-parallel to the field. This means a magnetic field doesn't exert a force on a stationary charge, because the velocity v would be zero. It only pushes charges that are already moving. Furthermore, the magnetic force is always perpendicular to both the velocity of the charge and the magnetic field itself. This means the force changes the direction of the particle's motion, causing it to curve, but it doesn't change its speed. Therefore, a magnetic field does no work on a charge. The direction of the magnetic force is found using the right-hand rule. For a positive charge, point your fingers in the direction of velocity, v. Curl them towards the magnetic field, b, and your thumb points in the direction of the force, F. For a negative charge, the force is in the opposite direction. Let's work through a practical example of a magnetic force. Imagine an electron moving with a speed of 3 × 10⁶ meters per second. It enters a uniform magnetic field with a strength of 0.5 Tesla. The direction of its velocity is at a 60-degree angle to the magnetic field. What is the magnitude of the magnetic force acting on the electron? First, let's identify what we're given and what we need to find. We know the charge of an electron Q. We have its speed v. We know the magnetic field strength, b, and we have the angle theta. To find the magnitude of the force, we use our magnetic force law. The force F is the magnitude of the charge times the velocity times the magnetic field times the sine of the angle theta. It's important to use the absolute value of the charge in this formula when you're just looking for the magnitude of the force. Now, let's plug in all our values. F equals the absolute value of negative 1.6 times 10 to the negative 19th coulombs, times 3 times 10 to the 6th meters per second, times 0.5 Tesla times the sine of 60 degrees. The sine of 60 degrees is approximately 0.866. Let's do the calculation step by step. F equals the absolute value of the charge, times 3 times 10 to the 6th, times 0.5, times 0.866. Multiplying the numbers and the powers of 10, we get a force of approximately 2.08 times 10 to the negative 13th newtons. This is a very small force, but in the microscopic world of electrons, it's powerful enough to dramatically change the particle's trajectory. If we wanted the direction, we'd use the right-hand rule. For an electron, a negative charge, the force would be opposite to what the rule gives for a positive charge. Let's quickly recap what we've accomplished on our journey through electromagnetism. We started with the fundamentals of electric charge and learned to calculate the force between charges using Coulomb's law. We then moved on to the concept of the electric field, which describes the influence a charge has on its surroundings. From there, we explored the energy side of things, introducing electric potential energy and electric potential, or voltage. We saw how voltage is the key to understanding the electrical pressure in a system and how to calculate it using a scalar sum. This led us to capacitors, the clever devices that store this electric charge and energy. We learned about capacitance and the energy stored within a capacitor's electric field. We then saw how these components come together to form circuits. We defined current, learned Ohm's law, and practiced simplifying complex circuits of resistors. Finally, we connected electricity and magnetism, introducing the magnetic field produced by moving charges. We learned to calculate the force exerted by a magnetic field on a moving charged particle. Electromagnetism is a vast and beautiful subject, but these concepts, force, field, potential, current, and magnetism, are the foundational building blocks. By understanding them, you've taken a significant step toward unlocking the mysteries of the universe and the technology that defines our modern world. I hope this lesson has been clear and helpful. Keep practicing, and the concepts will continue to solidify.